Hello, good morning students and my dear GATE aspirants of GATE 2026. This is Sekhar from M Sigma Gokulam and hope all of you are prepared well until now for the GATE 2026 examination. But in this video I want to give you the tips how to utilize this last 1 month. Exactly 1 month is there from today for the GATE 2026 examination, which is scheduled on February 14th. Okay, exactly 1 month before, 1 week before to that GATE 2026, we have the IES prelims also. ESC 2026 prelims examination is also there. Many of you will be writing that exam also. Exactly 1 week prior to the GATE examination, there is engineering services prelims examination. That is a very useful for the GATE mechanical, particularly all core branches students, because they will be testing exactly 1 week before how well they have prepared for the GATE. That is February 8th ESC prelims and 14th there is a GATE examination. But of course I will be coming with the detailed solutions for that ESC paper also on the February 8th. Still complete analysis of the paper, because we get the complete paper for the prelims examination, ESC prelims. I will be coming out with the detailed analysis of the solutions on the February 8th. Wait for that video. Okay, today's video I am going to explain about what are the last month preparation strategy for this GATE 2026. Okay, well, actually there are certain specific areas we have to focus more in this 1 month preparation. There are certain pockets we have to give an extra attention, extra focus to get the best score in the GATE 2026. I will go on the subject wise. What are those areas where we have to give extra focus? We have to revise time and again. We have to revise the time and again for those topics. What are those topics I want to highlight? And I would like to tell you what are the mistakes you should not commit during the preparation, and everything I will highlight in this video. So the main objective of this video is how to utilize the last 1 month at the best for the GATE preparation. Okay, so first I will start with the thermal stream, thermal and fluid sciences. It's where the first and important subject will be thermodynamics. So that the most important topics where the questions are definitely expected will be the first law and second law. That is a main core, that is a core part of thermodynamics lies in the first law of thermodynamics analysis and second law. In the first law of thermodynamics, we have the two things again, closed and open. This is first, actually when you attempt a thermodynamic problem, I have already said in my videos also, give the 3 inquiries about the thermodynamic problem. Ask yourself the 3 inquiries. What is the nature of the system? What is the nature of the process? What is the nature of the working fluid? Okay, that's 3 inquiries. If you do it, if you are able to identify those 3 inquiries, get the answers for those 3 inquiries, yes, you can easily start to solve the problem. In the closed system, we know that first law will be the written, which is applicable for any thermodynamic process. This equation is applicable for whether reversible or irreversible and whatever may be the working fluid. This equation is valid for any thermodynamic process, any working fluid. So if the process is reversible, then this will take a delta W, or this equation in the differential form. It could be written like this. And if the process is reversible, delta W is equal to PdV and delta Q is equal to TdS. If the process is reversible, okay. If process is reversible, actually this kind of a analysis is very important while attempting the thermodynamic problem. Nature of the system. This is valid only for the closed system, because in the recent examinations, GATE 25, 24, 23 is focusing more on the closed. Actually, in the earlier examinations, he was focusing more on the open. So in the open system, what is that equation? In the open system, SFE, steady flow energy equation. That because most of the thermodynamic systems are open, turbine, compressor, pump, nozzle, diffuser, etc. The majority of them are open. So more likely chances of the getting the problem from the first law is from the open than from the closed. But in the recent examination 25-24, he has asked for the closed system. Actually, sometimes in the closed system, system problem may be asked like this. Supposing in one examination is asked like this: there is a insulated chamber, there is a fan is churning. Inside we have the working fluid is ideal gas, because If you are able to identify the working fluid, like whether it's air or a hydrogen, etc., which are supposed to be an ideal gases, so dealing with ideal gas is easy. So in the thermodynamics, problem which is containing an ideal gas is dealing with that is quite easy, because this delta U will simply become for the ideal gas mCv delta T. For the ideal gas, any thermodynamic process delta U is equal to mCv delta T. You don't have to bother about the process, you don't have to bother about the system. Delta U is equal to mCv delta T and delta H is equal to mCp delta T for the ideal gas, which is generally air, hydrogen, nitrogen, all these are supposed to be ideal gases which obeys the ideal gas equation. PV is equal to MRT at all pressures and temperatures, right? So the in gate 25 also 25 or 24 he has asked the a problem containing a mixtures of ideal gas. I think 24 I guess. So mixture, again when you are dealing with the mixtures of ideal gas, what is that ideal gas law? Deals with the mixtures, Dalton's law of partial pressures. Okay, that if that is the number of, how to deal with the number of moles, what is the, when you are dealing with ideal gas, we have to combine so many concepts. We have the PV is equal to MRT, we have a delta is equal to mCv delta T, we have delta H is equal to mCv delta T. Supposing if this is air, we are churning the fan inside the inside that, which is fan is kept inside that closed system. So after you are done a certain work there, what would be the change in enthalpy? Question may come like this: what will be the change in internal energy? You can easily calculate. If you were able to calculate the delta T, we can calculate, get the change in enthalpy. We can calculate the change in internal energy from this formula if the working fluid is ideal gas. And you can definitely apply this equation, even though this process is irreversible, this equation you can apply, because I already said any thermodynamic process, this equation is applicable. So this kind of a clarification one should have. This you have to write all those tips. When you can write this process, when you can write this equation for any thermodynamic process undergone by closed system for any working fluid, even if you have the steam is here, you could still write this equation. Working fluid is steam, which is not an ideal gas, you could write this equation. So this distinguishing one should be able to understand. You have to write those tips as such. So if your problem is given like this way, you have to go in this direction. If the problem is given other way, you have to go in this direction. But that underlying concepts you have to catch up and write that salient points importantly. Okay. So and coming to this SFE, steady flow energy question, which is very, very important, very commonly being asked. This is a more prominent than this previous equation. This is more prominent, more famous, more commonly applied than this equation. This is applied for the closed only, but majority of the system and thermodynamic systems are open. So I should be able to write this equation more commonly for the nozzle, turbine, above all turbine, compressor. These three are the main things where the gate questions are usually focused. Turbine, nozzle, compressor. Pump is there, but that is not that important. Turbine could be steam turbine or a gas turbine, anything. You could write this. For any thermodynamic process, you can write. Any thermodynamic process. But only requirement is, because this is called as a SFE, steady flow energy equation, it should be an open system undergoing a steady flow process. What do you mean by steady flow? Things will not change with respect to the time. At any particular point, if the parameters do not change with respect to time, that process is called as a steady flow. Almost all the open systems will operate under the steady flow. There are few exceptions, like unsteady conditions are there, like a filling of the flask and emptying of the flask. They also asked the questions from that, but lesser. Most of the first law of thermodynamics pertaining to the open system come from this equation, usage of this equation. And very often the question comes from the nozzle. Okay. Nozzle is a device wherein the enthalpy or the total heat of the fluid gets converted into the kinetic energy without any heat transfer, without any external work done. Work transfer is zero, heat transfer is zero. You will get a high velocity kinetic jet of the fluid, maybe steam or maybe a gas. So, okay, so this delta H is being, the decrease in enthalpy is being observed as the increase in kinetic energy and neglecting the changes in potential energy. So, they have to write this equation for this and you have to identify the working fluid. If you are identifying the working fluid, mostly it will be air. Air is an ideal gas which obeys PV is equal to RT. And if the process is, again the process could be reversible or irreversible for but whereas this equation is applicable for any thermodynamic process, reversible or irreversible. So give a more attention for this. In this first thermodynamics, you have to give more attention to that. Q minus W is equal to delta U, closed system first law, and open system steady flow energy equation. Okay, if the process is reversible, still irreversible or irreversible, this equation is applicable. If the process is reversible, you will get one additional equation. If the process is reversible and adiabatic, means isentropic. If there is an isentropic equation, you can write this equation, P2 by P1 is equal to T2 by T1, but both the temperature should be in Kelvin. So we have to combine all these concepts to solve a problem of nozzle. We have asked so many times. If you look at the previous GATE papers, if you see 5 to 6 times the problems on this nozzle using all these equations. You have to use only either SFEE, which is applicable for any thermodynamic process. This is only strictly applicable for isentropic, that is reversible and adiabatic process, and this is an ideal gas equation. PV is equal to RT. PV is equal to RT. So you have to combine all these equations to solve this problem, but provided you have to take a particular care that both the temperatures should be in Kelvin. So give a more focus for the SFEE, and this equation is called NFEE. This equation is called as NFEE. This equation is called as SFEE. NFEE for the closed system. Okay. Yes, that is one topic. And coming to the more important topic in thermodynamics than the first law is second law. Most of the questions, what is the weightage of thermodynamics in GATE means usually 6 marks, rarely 7, very commonly 5, 6, mostly that will jump, sometimes 5, sometimes 6, like that. But definitely questions from these topics only, first law, second law, and entropy changes, majority of the questions. Sometimes pure substances also may ask. See, they don't leave any topic. Whatever the 6 marks allotted for thermodynamics, one question they may ask from the first law, and one question they may ask from the entropy changes, and one question they may ask from the Clausius inequality, which is a corollary of the second law of thermodynamics. So we have to be ready for all sorts of questions. But there are some topics which are more important than the others. I am highlighting those topics which are more important, which are very commonly asked, which will never be missed in for GATE examination. All those topics I am highlighting in this video. In the second law, very commonly asked thing will be the Carnot. Second law, and Carnot theorem analysis. That Carnot cycle, which is represented on the TS plane as a rectangle. Carnot, you have the Carnot heat engine, we have the Carnot refrigerator, right? So if the Carnot theorem, they says that thermal efficiency is only a T1 minus T2 by T1. Okay, T1 minus T2 by T1. If this is 1, this is 2. If this is a Carnot cycle, if this is T1, if this is T2, this Q1 is the heat supply and Q2 is the heat rejection. This could be written as 1 minus Q2. This kind of, see, only for the Carnot cycle, the thermal efficiency formula can be written in terms of the temperatures only. Any other thermodynamic cycle, like Otto cycle, Brayton cycle, or diesel cycle, we cannot write the thermal efficiency as a function of temperatures. That is a privilege for the Carnot cycle. Because no heat engine can have a more thermal efficiency than the Carnot. Okay. So this kind of analysis, you have asked in the recent examinations only to calculate the thermal efficiency of the Carnot heat engine, CHE, which is also called as the reversible heat engine. This is one thing. And very commonly they set a question that a heat engine driving a refrigerator or heat pump. A heat engine will be driving a refrigerator or a heat pump. Heat engine will be receiving a heat from some source and rejecting heat to the sink. This is the source. This is the sink, because any heat engine operates between the source and sink. One high temperature thermal reservoir and low temperature thermal reservoir. Generally, when you are setting the GATE question, they will use the word what will be the maximum amount of work you get. What is the minimum amount of heat rejected to the sink? whenever you are reading such kind of words in the gate problem, such wording, what is that wording? Maximum or minimum, that this kind of wording if you are seeing in the gate problem, yes, by default, by blindly we can apply the Carnot principle there. Because in the Carnot heat engine, highest thermal efficiency you are achieving, that means maximum work output will be you are achieving for a given heat supply, which means minimum heat is rejected to the sink. So whenever you are reading a problem, you containing these words like a maximum, minimum, think that that particular device is running on a Carnot cycle, maybe a original Carnot cycle or a reversed Carnot cycle. In fact, there is one more modification of this Carnot cycle, reversed Carnot cycle, which is going in the anti-clockwise sense. Any cycle running in the anti-clockwise sense, obviously it will be for the refrigerator or for the heat pump. Any cycle which is running the clockwise engine, that is for the heat engine. Any cycle, thermodynamic cycle running in the clockwise, it is meant for the heat engine. Any cycle running in the anti-clockwise like this, that is meant for the either refrigerator or heat pump. They do the same thing. Refrigerator or heat pump, their business is the same, but only thing is why two names are given based on the useful effect wanted. In the refrigerator, our main objective will be to extract as much heat as possible from the low temperature reservoir. Whereas in the heat pump, our main objective, main task will be how much heat will be rejected to the high temperature reservoir. But they do the same task, both refrigerator and heat pump. And there the cycle will be going in the anti-clockwise. Just like the Carnot heat engine has got the highest thermal efficiency, any Carnot refrigerator which is shown as a rectangle. See, Carnot cycle has got a shape of rectangle on the TS plane. If this anti-clockwise cycle is used for the heat pump or a refrigerator, that becomes a Carnot refrigerator or a Carnot heat pump, which will have the highest coefficient of performance. Just like thermal efficiency for the heat engine, COP for the heat pump. So we have to write these tips that where you may go wrong. Because my advice in this 1 month will be give as many tests as possible. Self-evaluation is very important. Self-assessment, self-evaluation, so that you can identify mistakes and plug those mistakes, plug those holes wherever you are weak, so that the journey will be smooth until the gate examination. So for plugging those holes, you have to evaluate yourself. For that, you have to give a frequent tests, as many tests as possible, you have to identify those gaps, the weak areas, and try to make them stronger. The mistakes what you are committing. See, a heat engine is driving a refrigerator. A refrigerator function will be, refrigerator or heat pump function will be to transfer heat from the heat from the low temperature reservoir and reject it to the high temperature reservoir. So the work output of the heat engine will be used to drive the refrigerator. Actually, that is, you see, this kind of a problems are very, very common. You have to be ready. One may be reversible, other may be irreversible. This may be reversible, this may be irreversible. But whenever you are seeing that word reversible, think that it is a Carnot, because Carnot cycle is the only reversible cycle you are dealing. In our thermodynamics, Carnot cycle is the only reversible cycle you are dealing, because there are two other cycles are there, but we never bother about them, reversed Stirling and reversed Ericsson, but they are very rarely thought of. But whenever you thought of a reversible cycle, think of the Carnot. Supposing if it is reversible, these temperatures will be given. So the efficiency of that heat engine can be calculated by using these temperatures, by using this formula. Supposing if this is reversible, operating on a Carnot cycle, then COP of the Carnot, you can again use the formula in terms of the temperatures. The speciality of the Carnot cycle is its efficiency and its COP depend only on the temperatures. So if it is a Carnot heat pump, then it will be TH by TH minus T. See, this kind of an understanding is very important to solve the problem thoroughly. Okay, you may be giving this heat, you may be asking you to calculate this heat. The problem can be set anyway. But as long as you are strong in the fundamental concepts, there is a very little chance that you go wrong. Very little chance that you may go wrong. So, because if your concepts are very strong, definitely you are likely to get 99% probability of correct answer. Okay. And one more thing, in the gate, the answers, particularly in NEIT type, multiple choice no problem. In the NEIT type, because you have to fill in the gap, at least after a decimal, 2 digits, minimum 2 digits, you should put in the question answer. You have to type it minimum in the virtual calculator. But you have to get after decimal minimum 2 digits. If you keep 3 digits, that is fine, but minimum 2 digits, we have to give a correct answer. You are getting 38.572. Some students may putting 38.45. No, you have to keep 38.57. Minimum 2 digits after decimal. Okay. Yes, this is one important module of the second law, where your Carnot cycle is emphatically being asked. And again, we have the Clausius inequality. They are repeatedly asked here, Clausius inequality. This is the corollary of the second law of thermodynamics. Cyclic integral of delta Q by T is less than or equal to 0. Less than sign for the irreversible cycle, equality sign for the reversible cycle. Okay, cyclic integral of delta. For any thermodynamic cycle, this equal. If it is greater than 0, it will simply violate the second law of thermodynamics. This is being asked, particularly when a heat engine, when a device is rejecting heat, receiving heat from 2 reservoirs and rejecting heat to 1 reservoir, which are at different temperatures. Okay, this is Q1, this is Q2, this is Q3. Well, if the device is reversible or irreversible, based on this we can calculate. Okay, they may ask you to know whether the device is reversible or irreversible. If the device is reversible, is it a reversible heat pump or a reversible refrigerator? You are a reversible heat pump. That also you will ask. First, they will ask you to check whether it is a reversible or irreversible by using this Clausius inequality. If so, if it is a reversible heat pump or a reversible refrigerator, that also you have to identify. That kind of questions are very, very, very common. This round only indicates that it is meant for a cycle, thermodynamic cycle. Cycle means it could be a clockwise cycle or anti-clockwise cycle. That means this equation is applicable for both heat engine, refrigerator and heat pump. Okay, so this is the Clausius inequality, very, very important thing in the second law. Okay. Coming to this entropy. Entropy is another big area, another important thing. Many people understand energy easily, but entropy, they think, what is this entropy, how to physically interpret that. Very simple. Entropy is a thermodynamic property whose change in the thermodynamic universe will decide whether the process undergone in the universe is reversible or irreversible. Because according to the second law of thermodynamics, delta S of the thermodynamic universe, that is delta S of the system plus delta S of the surroundings, if it is greater than 0, that means universe means what? System plus surroundings. If it is greater than 0, I will decide the process as irreversible. If it is equal to 0, I will say that the process is reversible, because the entropy of the thermodynamic universe will never decrease. Either it will increase or remains constant. So if it is equal to 0, I will decide. Actually, there are two symbols. If it is equal to 0, that will means it is irreversible. If it is greater than 0, it means it is irreversible. So I could define the nature of the process, whether reversible or irreversible, based upon the change in entropy of the thermodynamic universe during that process. Not for the system, not for the system. A thermodynamic process, in a thermodynamic process, entropy of the system may decrease or may increase. Entropy of the universe, entropy of the surroundings. In a thermodynamic process, in any thermodynamic process, there is some heat interaction or work interaction between the system and the surroundings, right? During that process, entropy of the system may increase or may decrease. And during that process, entropy of the surroundings may increase or may decrease. But if you combinedly add both of them, change in entropy of the system and surroundings algebraically, that sum will be always greater than 0 if the process is irreversible. If it is equal to 0, yes, blindly I can say that it is a reversible, like in case of a Carnot heat engine cycle. because Carnot heat engine cycle is a completely reversible cycle. It will not create any entropy in the thermodynamic universe. So, if entropy is generated or created or produced inside the thermodynamic universe, it is an indication that the process is irreversible. If there is no entropy generation, fine, it is a reversible, but entropy of the universe will never decrease. Right. So, this is I'd like to advise you that change in entropy of the general formula for the entropy of any process, there is any process we can calculate by integrating, that is delta q by t integral. Okay. For that we can TdS is equal to du plus pdv, which are valid for any thermodynamic process, because these are the relation among the thermodynamic process. TdS is equal to dH minus VdP. Use these TdS relations to calculate the change in entropy for any thermodynamic process undergone by a ideal gas. Supposing if it is an ideal gas, you could write this as CVdT, because for ideal gas du is equal to CVdT, for ideal gas dH is equal to CPdT only for the ideal gas. Use this relation and bring the T right side and then integrate, you will get the change in entropy formula for any thermodynamic process, because these equations are valid for any thermodynamic process. Okay, ds is equal to delta q by T is valid only for the reversible process. ds is equal to delta q by T is only valid for the reversible process. Okay, but these two equations are valid for any thermodynamic process. Why any thermodynamic process? Because they contain only a relation among the 5 thermodynamic properties. Any property relation is independent of the path followed. So, the two TdS relations are valid for any thermodynamic process. Therefore, by using these two equations, you can calculate the change in entropy for any thermodynamic process undergone by an ideal gas. For ideal gas, we have this privilege, du is equal to CVdT and dH is equal to CPdT, right. So, this is the 3 important focus areas where you have to give extra attention is first law, second law and entropy changes. These are the main thing there, okay. And apart from that, you may have to deal with the pure substances also. Pure substance is slightly difficult, because we have to deal with the tables. You have the HFG, HF, SF, SFG, how to calculate. No, this particularly pure substance means properties of steam, nothing new. That is the properties of this steam, like how to evaluate the change in entropy, because here that you have to cleverly denote the properties HF, SF. We have to identify the properties here, HG, SG, VG. We should how to cleverly pick up the data, property data given in the problem. That is very important for the pure substances analysis. This is the HFG or latent heat. When you talk about the pure substances, very important relation is Clapeyron relation. Clapeyron relation. That will give the rate of change of the for a saturation, okay. So, this Clapeyron relation will change about, because as you know, as the pressure increases, boiling temperature or the evaporating temperature also will increase. How does it change is given by this Clapeyron relation. It is connected to the latent heat, specific volume, etc. Okay, that relation we has asked in the recent years only, Clapeyron relation. It tells about a link between saturation temperature and saturation pressure and the latent heat, and also of course the specific volume changes, Vf and Vg. So, that is a relation containing all these parameters, right. When you talk about the pure substances, one should be having a clear idea about the triple point, the saturation temperature, saturation pressure, how they are linked, HFG, SFG, because we know that HFG is equal to SFG. This relation we should never forget, T saturation in Kelvin. So, this relation we have to remember again, because HFG is nothing but the latent heat of vaporization. So triple point, critical point. This is a critical point where the latent heat of vaporization is 0. Okay. So this is all about the thermodynamic important topics where you have to give extra focus. First law, second law, entropy changes, and fundamentals of the pure substances. When I talk about the pure substances, if you learn thoroughly the properties of steam, you can do any problem. Thermal power plant, like a Rankine cycle analysis, you can do any problem. You can do any problem of the refrigeration in the vapor compression cycle, VCR cycle. All these things become easy if you learn this pure substances chapter. So give some extra time to this pure substances analysis. Okay, not a difficult topic, but one should be able to cleverly pick up the data from the given table. You will be given a table of containing properties where you will be seeing PSAT, TSAT, HF, HFG, HG, SF, SFG, SG, like that. So you have to cleverly pick up that particular value from the table and substitute in the problem. Okay, so that wisely you have to pick up. But this is very useful to solve. I said all three topics. One in thermodynamics chapter, other in the Rankine cycle analysis, other in the vapor compression refrigeration system. Right. This is all about the thermodynamics. Then I will go to the another important subject, fluid mechanics. Yes, the weightage will be around 6 to 7. Again, 6 to 7 marks. What are the most important areas? Means first weightage I give to the fluid kinematics, and I am talking about the weightage based and importance based fluid kinematics, where you deal with the steady flow, unsteady flow, rotational, irrotational, compressible, incompressible, laminar, turbulent, all these classification of the flows. First of all you should know. First of all you should know the classification of the flows. Okay. In this kinematics, fluid kinematics, you will be talking about the stream function psi, velocity potential function phi, and the equation of the streamline. Very often this is asked. Right, you will be given the velocity field ui bar plus v j bar plus w k bar. U and v and w are the velocity components. So you will be given u, v and w, the velocity field, mostly 2-dimensional, very rarely 3-dimensional, but mostly 95% cases you will be dealing with the 2-dimensional flows, where u will be given, v will be given. What is u and v? Velocity components. So given those velocity components, he will ask you to get what is the equation of the streamline. Equation of the streamline. Streamline is an imaginary line who, if you draw a tangent to that, you will get the velocity component. Obviously, what is the equation of the streamline? Dy by dx. Slope of the tangent will be v by u. So from here you have to begin the problem and finally integrate the equation. You have to get the equation of the streamline. This is a velocity potential function. This is a streamline, a stream function. This is a stream function. Stream function is that function which remains constant for a streamline. Velocity potential function is that function. Velocity potential function is that function which remains constant for a equipotential line. That equipotential line and constant stream function line are orthogonal to each other. They cut orthogonally to each other. So these are the very important. And you have acceleration components, that is convective acceleration, local acceleration. Local acceleration. What is the distinguishment? For this local acceleration is 0 in the steady flow. This convective acceleration is 0 for the uniform flow. So first of all you should understand what is uniform, non-uniform, steady, unsteady. Okay, laminar, turbulent, rotational, irrotational. These concepts you have to be very thorough. Okay, in the kinematics chapter. Maximum weightage, maximum importance I give it to the kinematics first. Very often the questions will be asked. And continuity equation, right? Divergent V is equal to 0. This is a continuity equation for a steady 3-dimensional incompressible flow. This equation is called equation of continuity. For a steady incompressible 3-dimensional flow, divergent V is equal to 0. Curl V is equal to 0. This is for the irrotationality. Okay. So that all this comes under the kinematics. Give a extra time, give an extra focus for this during the revision of during this 1 month for this particular chapter. Give an extra time. Continuity equation is also written like this: dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0 for steady three-dimensional incompressible flow. For steady three-dimensional incompressible flow, this is the continuity equation. And whenever there is a fluid flow existing, this continuity equation, which is nothing but the law of conservation of mass. Continuity equation is nothing but the law of conservation of mass must be satisfied. So that is that is in the fluid kinematics, because as I said, given the velocity potential and you may ask you to calculate what is the magnitude of the velocity, because velocity potential is, how do you define the velocity potential, by the by? Whose negative derivative with respect to any direction will give the velocity component in that direction. How do you define the stream function psi, whose derivative with respect to a new direction will give the velocity component in the perpendicular direction? Dou psi by dou y is minus u. Okay. And slope of equipotential line and slope of the constant stream function line, the product will be -1, and therefore they cut orthogonally. Constant equipotential line and constant stream function line, they cut orthogonally at every point in the flow field except at the stagnation points. So they cut orthogonally because the product of their slopes of those respective lines becomes 1. Okay. So right, this is all about the kinematics. Then comes to the you have very important chapter, fluid dynamics, where you talk about the Euler's equation, Bernoulli, Euler's. This is the law of conservation of momentum. Applying the Newton's second law of motion to a flow field, you got this Euler's equation of motion, where you consider only two varieties of forces: gravity forces and pressure forces. In the Euler's equation of motion, we consider only gravity and pressure, assuming that the fluid has zero viscosity. Okay. First importance I give to the kinematics, second important to the fluid dynamics. Extra, I mean to say, they carry the extra weightage, most likely to be asked in the gate, because they are the core areas for the fluid mechanics. Euler's equation of motion, that is a dp by rho plus vdv for the streamline plus dz dat is equal to 0. Pressure, density, velocity, acceleration due to gravity and elevation. Z is the elevation, datum measured from the datum line. So this is the Euler's equation of motion for the streamline. But if you write along the x, this can be written in another way also. X minus 1 by rho into dou p by dou x is equal to ax, convective axis for steady flow, convective acceleration along the x direction, which is written as u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. So this is the Euler's equation of motion for along an x direction, whereas this is a body force potential along the x direction. This is the pressure gradient along the x direction. This is the convective acceleration along the x direction. In one of the gate examination, they are asked what is the pressure gradient along the x direction. What is the, and similarly you can write for the y direction also. So the pressure gradient we have to calculate from the given data of the u and v and w. So that kind of questions are very common. Kinematics is slightly kinematics and dynamics, some slightly mathematical. One should be able to know how to integrate, how to get the constant of integration from the boundary conditions. So that they must be clever enough in integrating differentiation, partial differentiation and partial integration, and then how to get the constant of integration. One must be thorough in solving the problems of kinematics. By integrating this, you get the Bernoulli, the central concept of fluid dynamics, Bernoulli's equation, law of conservation of energy, Bernoulli's equation, P by W, V square by 2Z plus Z is equal to constant. Give an extra focus for this. Very often, very frequently, the questions are asked in the Bernoulli's equation. That dealing with the Bernoulli equation is quite easy because all are scalar quantities. Kinetic energy, but all are they are the energies. Each thing is an energy. Energy is a scalar quantity. Don't bother about the direction. This is a pressure energy per unit weight, this is a kinetic energy per unit weight, this is a potential energy per unit weight. Therefore, it is something talking about a total energy carried by the fluid. Between any two locations, the total energy remains constant, neglecting the loss of head. If there is a decrease of energy, yes, that means there is a loss of head. So, it is constant if no loss of head. If loss of head is there, why loss of head? Due to friction. So, a Bernoulli equation and its application. Very commonly, the two applications I give the most important, venturimeter and petard tube, only two. This is for measurement of discharge, Q. Q means discharge here, and this is for the measurement of velocity of the flowing fluid, whether it is a open channel, whether it is an open river or a closed pipe. This petard tube can be used to measure the velocity of the flowing liquid, maybe in a open canal, open channel, or rather maybe in a closed pipe. How do you make use of this Bernoulli equation? These two are the clear applications of the Bernoulli, to measure the discharge and to measure the velocity of the flow. Right, this give an extra focus to this, okay. And think that the loss of head, which mostly happen due to the friction, that will always happen in the direction of the flow. If there are two locations are there, if you want to decide whether the flow is from, this is 1, this is 2, if the flow is from 1 to 2 or 2 to 1, calculate total head at 1, calculate total head at 2. Flow always occurs in a direction in which the total head of the fluid keeps decreasing. If the total head at 1 is more than the total head at 2, that means flow is from 1 to 2. If the total head at 2 is more and total head at 1 is lesser, flow is from 2 to 1. The total head, the flow occurs in a direction in which the total head, that total head means sum of these three. This is pressure head, velocity head, datum head. The sum is called as the total head. Give an extra time for revising this Bernoulli equation and its applications. Then comes the impulse momentum equation. This is something connected with the forces. Impulse momentum means Newton's second law only, application of the Newton's second law. So, for writing the impulse momentum equation, give an extra, how to take a control volume, that try to learn that thoroughly. I have explained in my videos very clearly, in my fluid mechanics videos. Consider a control volume and identify all the forces acting on that fluid control volume and give a direction, because it is a vector equation. Impulse is a vector, momentum is a vector, it is a vector equation, sigma fx. The net algebraic sum of all the forces acting along a given direction must be equal to the max. That is a Newton's second law, right? And similarly, sigma fy, the net algebraic sum of all the forces acting on a fluid control volume along a given direction must be equal to the mass times acceleration along that direction. That means if a fluid is flowing in a pipe, there what is the rate of momentum entering, what is the rate of momentum leaving? Rate of momentum leaving minus rate of momentum entering will give, in a particular direction, will give the, if this is the control volume, if this dotted line is the control volume, the rate of momentum leaving here, rate of momentum leaving minus rate of momentum entering along a given direction must be equal to the forces along that direction. I repeat once again. What is the momentum leaving means what? Rate of momentum. What is the meaning of that rate of momentum? Mass flow rate into velocity. We know that momentum is mass times velocity. But if you put a dot, mass flow rate into velocity, that gives the rate of momentum, which is a vector. It is a vector quantity. You have to cleverly identify the direction of the momentum and in what direction the forces are acting, and all these things we have to give an extra thing, because this is slightly difficult as compared to the Bernoulli's. Bernoulli's is a scalar equation, Bernoulli's equation, because all are scalar quantities, but whereas this is a vector equation based on which we can calculate what is the forces exerted by the pipe bend on the control volume, or in a impact of jet also. In many cases, impact of jet being asked. A open flat is hit by a jet of water. How much force the jet will exert over that flat plate? This is a flat plate. From here we can extend this analysis to the turbines also. By changing the shape of the plate to the vane, we can even calculate what is the force exerted by the jet on the curved vane or on the flat plate by using the same principle, impulse momentum equation. So totally we have three conservations: conservation of mass, continuity equation; conservation of energy, Bernoulli's equation; conservation of momentum is impulse momentum equation, Euler's equation of motion, and by the way, Navier-Stokes equation of motion. All these are conservation of linear momentum, which is a application of impulse momentum equation. Euler's equation of motion, Navier-Stokes equation of motion, they are all the conservation of linear momentum. The only difference between Euler's and Navier-Stokes is Euler's equation of motion considers only pressure and gravity forces, whereas the Navier-Stokes equation of motion consider one extra force called viscous force. Euler's equation assumes fluid is ideal, inviscid, non-viscous, whereas Navier-Stokes equation assumes fluid has got viscosity, real fluid, not ideal fluid. Okay. So these are the main core areas where you have to give next, and of course we have the very recently the flow through pipes very frequently being asked. Flow through pipes, incompressible flow through pipes, laminar flow, turbulent flow, laminar, how do you distinguish the laminar or turbulent? By using the Reynolds number. Reynolds number is the only number which can decide flow is laminar or turbulent. And head losses due to friction. Okay, we have the Huygens-Poiseuille equation, 32 mu VL by W d square. We have the turbulent equation, HF is equal to FLV square by 2GD, Darcy-Weisbach equation. This is Huygens-Poiseuille equation. And what is the velocity distribution, what is the shear stress distribution. So that also we have to understand. Particularly whenever you are dealing with the flow through pipes, first immediately check whether the flow is laminar or turbulent. First by using the Reynolds number. Sometimes in the question itself may be given flow is laminar. And interestingly, this Darcy-Weisbach equation, which is meant for calculating the head loss due to friction, is valid for both laminar flow and turbulent flow, whereas this is valid only for the laminar flow, Huygens-Poiseuille equation. Okay, so this what is the velocity distribution? This is axis symmetric parabolic velocity distribution. What is the shear stress distribution? What is the shear stress? This is the shear stress distribution. The shear stress varies linearly with respect to radius. This is the velocity distribution. This is the shear stress distribution. Tau is a function of r, u is a function of r in laminar flow. Here the velocity distribution is either a logarithmic, I can say, velocity distribution. Okay. So dealing turbulent flow is slightly difficult, but this this Darcy-Weisbach equation is universally accepted. Darcy-Weisbach equation, this F is called as Darcy's friction factor. Darcy-Weisbach equation is valid for both the laminar flow and turbulent flow. It is commonly used for turbulent, but also valid for the laminar. Particularly for the laminar flow, that friction factor F will become 64 by Re. So all these things in friction factor depends only on the Reynolds number here, whereas in the turbulent flow, friction factor depends not only, friction factor is a function of not only the Reynolds number but also on the relative roughness of the pipe. So all these things you have to consolidate in a notes while repeating, while giving the final examination. Okay. And also is recently being asked flow pipes in series, pipes in parallel. In gate 25, I think he has asked the pipes in parallel. This is pipes in parallel. This is when in the pipes in parallel, Head loss due to friction is same for both the pipes, but the discharges will be different. Whereas in the pipes in series, when pipes in series, discharge is same throughout, but the head loss due to friction will be different. That is the main thing. In pipes in parallel, HF is same for all the pipes. But discharges, this is Q1, this is Q2. Total discharge will be Q1 plus Q2. Here, discharge is same for all the pipes. Q1 is equal to Q2 is equal to Q3. But HF1 is not equal to HF2 is not equal to HF3. So that linkage, we have that difference, pipes in series and pipes in parallel, you have to highlight. And then comes the boundary layer. This is a topic we should not neglect, because this is the one which is useful for the heat transfer also, where the weightage will be quite higher for the heat transfer. If you know boundary layer here, it will be again useful for the convection chapter of the heat transfer. Flow, the boundary layer, flow over flat plate, whether the flow is laminar, local Reynolds number, Vx rho by nu, and again how the shear stress will vary. That the local wall shear stress here, at this point we have the local wall shear stress. How the shear stress will vary? Tau wall is directly proportional to the 1 by root x. These kind of relations. How to calculate the boundary layer thickness? Delta is a function of x. Delta is a function of x. This is x direction, this is y direction, this is x direction. How the boundary layer grows? When this boundary layer will be laminar, when the boundary layer will become turbulent. So we have to calculate the local Reynolds number. If the local Reynolds number is less than 5 lakhs, you brand it as the laminar boundary layer. If it is greater than 7 lakhs, you brand it as the turbulent boundary layer. So this distinguishing how do the local wall shear stress varies with x. How the boundary layer thickness varies with x. Delta is directly proportional to the x to the power of half. All these things boundary layer, try to learn thoroughly. Okay, the main thing in the FM, again I will repeat, kinematics of fluid flow, dynamics. In the dynamics of fluid flow, you are dealt with the Euler's equation, Navier-Stokes equation, and again Bernoulli's equation and its applications, applications of Bernoulli. Then comes the impulse momentum equation to calculate the forces in the pipe bends and also the impact of jets. Or sometime one gate has given water is being released from a tap. It is falling, water is falling in a container, the container is kept on a weighing balance. At some instant, what is the reading observed in the weighing balance? So that kind of a question can be solved by using the impulse momentum equation. So impulse momentum equation, Bernoulli's equation, and Euler's equation. So they are the main components of the fluid dynamics. Then comes the flow through pipes and the boundary layer theory. And of course, we have the dimensional analysis in GATE 2024. In the dimensional analysis also a question is asked, but we have to just know the Buckingham pi theorem and Rayleigh theorem. Okay, Rayleigh theorem is very simple. Buckingham pi theorem he has asked once. Okay, the two theorems are there, Buckingham pi theorem and Rayleigh theorem. Buckingham pi theorem and Rayleigh theorem. And the 5 numbers, only we have 5 numbers there, Reynolds number, Euler number. He has asked once in Froude number, ratio between inertia force by gravity forces. And then we have the Weber Mach number. Mach number is a very important, because in the recently about 4 or 5 years back, compressible fluid flow is introduced. There comes the Mach number and then Weber number. Just to know about the definitions. Most important is Reynolds and the Mach number, because this Mach number is the one which we deal in the compressible fluid flow. What do you mean by compressible fluid flow? If the density is a function of pressure, then it becomes compressible fluid flow. One question is very recently is being asked. Every recent gates for last 22, gate 23, 24, 25, 25 also I think he has asked. One question is coming from the 1 mark or 2 mark is coming from the compressible fluid flow, where you deal with the Mach number, normal shock. What will happen to the fluid during the normal shock? So in a convergent divergent nozzle, the shock could happen only in the diverging portion. When a supersonic flow, like if m is greater than 1, supersonic flow, m is less than 1, subsonic flow, if m is equal to 1, sonic flow. This normal shock could happen only in the diverging portion when a supersonic flow abruptly becomes a subsonic flow. That's it. So, with some clues, with some information, you may not know the complete details. What I mean to say is, you may not go dig deep into the compressible fluid flow dynamics, but with some reasonable concepts and reasonable information, logical information, you will be able to answer most of the questions, even though you are not well off with the thorough knowledge, deep knowledge of the compressible fluid flow. Okay, because most of the equations are governed by this is the dA by A is equal to dV by V into m square minus 1. That means this will decide the change in area, shape of the device. If m is less than 1, this will be negative. This will be negative means dV, this will be negative. If m is less than 1, subsonic flow. That means is a negative. My dV is negative means this is negative means to get a, that means as the dA is, as area decreasing, velocity will be decreasing. So, like that. So, based upon this equation, you will be able to decide as the area increases based upon the Mach number. Based upon the Mach number, as the area increases, what will happen? Suppose if this is there, this is a nozzle. This is see. If dV, if you want the dV to be positive, this minus comes here, dA will be decreased. This is a nozzle. This is a diffuser. Generally, in the subsonic flow, if m is less than 1, from this equation you will get this. Here the dA is negative. Here the flow is like this. Here the dA is positive. Okay, diffuser means what? Velocity will be decreasing. What? Not even by nozzle, velocity will be increasing. Now, nozzle is a device where the velocity keeps increasing in the direction of the flow. Exactly opposite is diffuser. But this is a convergent divergent nozzle. This is a convergent divergent nozzle. A convergent divergent nozzle will be used to obtain the supersonic velocities at the exit of the nozzle. A convergent divergent nozzle, the main important thing in the compressible fluid flow is the convergent divergent nozzle will be used to obtain supersonic velocities at the exit of the nozzle, that is m is equal to greater than 1, Mach number greater than 1. So, this is the main topics in the fluid mechanics. Then comes the another very prominent subject called as the heat transfer. Weightage will be around 7 to 8 marks. In GATE 22 he has asked about I think 12 marks. 11 or 12 marks he has asked in GATE 22. But usually its weightage will be 7 to 8. Sometimes it may touch 9 also, depending upon the IIT who is paper setter and all that. Usual common average is 8. 4 chapters: conduction, convection, radiation, heat exchangers, out of which heat exchangers is the easiest topic because only 2 methods are there. Just focus on 2 methods: LMTD method, effectiveness NTU method. That's it. Heat exchanger is the easiest because only 2 methods of problem solving: LMTD method and effectiveness NTU method. Conduction, convection, radiation, heat exchangers, right? Only 4 chapters, out of which this is the only 2 methods: LMTD method and effectiveness NTU method. That's all. So, heat exchanger is over. Conduction is the biggest chapter among the remaining 3, and but it's easy only. But you may ask the questions about the composite slabs, composite cylinder, and all the heat transfers are one dimensional only. Sometimes mostly K will be constant, rarely K may be variable, thermal conductivity may be variable. Conduction is easy chapter only. Okay, where the most important focus you have to give regarding the critical radius. Critical radius, very frequently asked question. Critical radius of insulation, give a and Biot number. Biot number, of course, in the unsteady state conduction, lumped heat analysis, unsteady state conduction, Biot number will be definitely asked. Only Biot number, and of course, one more number is also there, Fourier number. These two numbers will be dealing with the unsteady state conduction, where the temperature becomes a function of time. Remaining rest of all the topics are steady state only. Unsteady state only in the lumped heat analysis we deal. The entire subject we assume that the conditions are steady, except in this topic called unsteady state conduction, where we deal with the Biot number and Fourier number, two dimensionless numbers we get in conduction chapter. And of course, heat generation. Very often in conduction chapter, recently gets very often the questions being asked in the heat generation. When heat is generated, Q dot, uniform heat generation, how the temperature distribution, is it a symmetric or is it an unsymmetric? Is it an unsymmetric? Well, if it is unsymmetric, where you get the maximum temperature in the slab? These questions are frequently being asked and again will be asked. Heat generation, repeat that, look into my videos. Heat generation case, so many problems I have asked, and in the recent gate also give a more focus in the conduction chapter, heat generation, critical radius of insulation, and lumped heat analysis, where we deal with the Biot number. Okay, that's it, the main three part of. And composite slab, composite cylinder, they are easy only how to construct a thermal circuit. Conduction thermal resistance for the slab, cylinder and sphere, B by Ka, ln R2 by R1 divided by 2 pi Kl. All those conduction resistances for a slab, cylinder and the sphere, try to evaluate, and we just try to know how to construct the thermal circuit. Because totally 4 resistances are there. In the conduction chapter, there will be 4 resistance. Conduction resistance offered by the slab, conduction resistance offered by the cylinder, and conduction resistance offered by sphere, 4 pi K, R1, R2, and finally we have the one convection resistance. This is only the convection thermal resistance. Convection thermal resistance. So only 4 resistances in the conduction chapter, and we have to know cleverly how to construct the thermal circuit. In this heat generation, no need of circuit, you can't draw the circuit also. Never try to draw in the thermal circuit in the heat generation cases, never attempt. Only when there is no heat generation, we can construct the thermal circuit and obtain the temperatures, like obtain the temperatures at this location, interface, or here, if this is the direction of the heat transfer. So one time both sides there may be convection, or only one side convection, like that. In recent gate examination, he is combining the conduction, convection and radiation. All 3 modes he is combining. Very cleverly setting the paper. Suppose that there is one slab. Some solar radiation is falling here. There is some fluid coming here. See the problem. This fluid is coming. This is a radiation falling upon the upper surface of the plate. And that radiation falling, some heat will be convected here to the fluid, and the balance heat, will go to the slab and gets conducted, and through the bottom slab it is convected to the other side fluid. This kind of a problem is asked. Radiation is falling and certain radiation is absorbed here, and that heat is being convected, some heat is convected to the fluid, and the balance heat will be conducted through the slab, and he is asking you to calculate what is the bottom side temperature given this temperature. So that kind of a problems he is wisely setting. Combining. So we have to understand, particularly for such problems, we have to understand how to write the energy balance. Energy can neither be created nor destroyed. So that principle we have to wisely apply. In one other gate examination, he has asked like this. There is a heat generation here. Only in the central slab there is a heat generation. There is no generation here in the other 2 sets. Only generation here. This heat generated in the central slab, it is conducted here, and finally convected here. So this kind of a problems is asked. And sometimes he is asking there is a heat generation in the slab and there is a vacuum here. There is a vacuum. When there is a vacuum, obviously heat will be only radiated here. So he is combining the concepts of conduction, radiation, or otherwise conduction, convection, radiation. All these things he is clubbing and asking the questions. So be ready for that kind of questions. Try to solve 4 or 5 problems in this kind of things. He is cleverly combining either 2 modes of heat transfer, sometimes all the 3 modes of heat transfer, conduction, convection, radiation. So for any, whether he combines 2 modes or 3 modes, the underlying principle to solve the problem is only one: law of conservation of energy. Energy can neither be created nor destroyed. Assuming steady state, whatever is being generated, that must be given off to some other sink. To maintain the steady state, whatever is being generated inside a certain control volume, all that must be dissipated, either a conduction mode or a convection mode or a radiation mode, to some other sink. So that concept, if you keep in mind, if you apply that concept, any problem can be solved. Right, this is about the conduction there. Then comes the radiation. In the radiation, thermal radiation, the most important topic, first preference I give it for the shape factor. I think in the last 25 years of GATE, I have seen these shape factor questions at least 17 to 18 times. So many questions being asked, shape factor. When you deal about the shape factor, the most important relation is reciprocity relation. A1 F12 is equal to A2 F21. That point you have to remember. And the summation rule. Summation rule. The 3 rules are there in the shape factor. And again, principle of superposition. If with the help of these 3 rules, principle of superposition, summation rule, and reciprocity relation, with 3 relations we can solve all the problems of shape factor. Okay, first priority, first top focus you have to give it to this. Then comes the radiation networks. Once you know radiation, how to construct the radiation networks, we should be able to calculate we will be able to solve any radiation problem. There are 2 kinds of resistances will come: surface resistance and space resistance. And again here I will use the concept of the black body. Black body, definition of the black body, Stephen Boltzmann. Actually there are many laws of radiation are there, out of which 2 laws are very important. One is Stephen Boltzmann law and another is Wien's displacement law. Wien's displacement law is asked 2 to 3 times. Both are applicable for the black body only. Wien's displacement law and the Stephen Boltzmann law for the black body. Black body MCU power will be sigma T to the power of 4. And the lambda m into T is equal to constant. This is the Wien's displacement law. This is also frequently being asked. And radiation, try to understand how to construct a radiation networks. Okay. While constructing radiation networks, concession will always be given like this: one body may be black. If a body is black, its surface resistance is 0. If a body is black, its surface resistance is 0. Or if the area of the surface is very large, because surface resistance formula will be 1 minus epsilon by epsilon into A. This surface resistance will be 0, either epsilon is 1 or epsilon is 1 means what? Black body. For black body, emissivity of the black body will be 1. If emissivity is 1, surface resistance of the black body is 0. One more reason is there. The surface resistance is 0 if the area is infinity, like a large surroundings. So while constructing radiation networks, particularly in the gate oriented problems, most of the times he is setting the question in such a way that surface resistance automatically becomes 0, either by making the body black or by making the area very, very large. Okay. So that kind of a observation you may see in all those gate problems where we need to use these radiation networks to solve the problem. Right. So this is the main thing, and of course laws of radiation, I said Stephen Boltzmann law, and of course the Wein's displacement. One more law is also there, Planck's law of thermal radiation, but that is not that important. And most of the radiation questions, radiation problems will come from the only two main formula are there. Two infinitely large planes, epsilon 1 and epsilon 2, how to calculate the radiation heat exchange. Q122 net is equal to sigma T1 power 4 minus T to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So that is infinitely large planes. And one more case, case 2 formula I call, when a large two concentric large concentric cylindricals are there, one by epsilon 1 plus A1 by A2 into 1 by epsilon 2 minus 1. This, please remember these two formulae, you can solve most of the gate radiation problems. But only thing is, these here F12 is equal to 1, F21 is less than 1. Here both the shape factors are 1 because they are infinitely large planes. Since they are infinitely large planes, both the shape factors are 1. Here one shape factor is 1 and other shape factor is less than 1. This formula, whatever the case 2 formula I call, is applicable for all the radiation heat exchange cases between two surfaces whenever one shape factor is 1 and other shape factor is less than 1. Yes, this is all about this radiation. Remember these two formulae. And when one shape factor will become 1, when one body is completely surrounded by another body, when one body is completely surrounded by another body, the shape factor of the inner body with respect to the outer body will automatically become 1. So under that circumstances, this formula is applicable. And even when T2 is greater than T1 also you could write same formula, but only thing is you will get a negative answer. That negative answer only means that net radiation heat transfer is from 2 to 1. If T2 is greater than T1, obviously net radiation heat transfer is from the higher temperature to the lower temperature. That means net radiation heat transfer from the outer surface to the inner surface. But formula will not change. Whether T1 is more than T2 or T2 is more than T1, never try to tamper the formula. Formula remains the same, provided F12 is equal to 1 and F21 is equal to 1. Please note that while solving the radiation problems, shape factor problems, numbering is very, very, very important. Which surface is which number, we have to cleverly identify and then proceed with the problem. Because to solve a problem, you are having 4 minutes or maximum 4 minutes in our hand. In those 4.5 minutes, maximum 5 minutes we can say, we have to cleverly read the problem, understand the concept, apply the relevant problem without any errors, and do the calculation and finally put that answer there. So all this will take 4 to 5 minutes there. But to quickly respond to the question, one must have a clear understanding, a clear concept in your mind. What may be the possible errors you may commit, you have to understand. That will be obtained only by making the short notes and by practicing the problems and by giving the frequent tests. Okay. Right. This is a radiation. Then comes the, people think that convection is tough. Actually, it is the easiest chapter, provided you have some clues. Generally, when you talk about the convection, only two kinds of problems will come. The algorithm goes like this. The algorithm means how to first identify the geometry. I am telling about the algorithm of solving the convection problem. Geometry means what? Whether it is a flow over flat plates or flow through pipe. First identify that. This is called internal flow. This is external flow. Because analysis will be different. The type of formula here and here will be different. This is the flow. Okay. In any convection problem, your main only task will be how to calculate the H. That's it. Final object will be to get the convection heat transfer coefficient H in watt per meter square Kelvin. Okay. First, then establish the Reynolds number. Calculate the Reynolds number. What for? To decide the flow as laminar or turbulent. You have to first make out laminar or turbulent. After getting that, then if it is a flow over flat plate, we got a different relation. We got the flow through pipes, we got a different relation. Again, in the flow through pipes, you got two different things will come. This is a constant heat flux situation, constant pipe wall temperature, constant pipe wall. This is a different condition. Two different conditions may in almost all the gate problems in the recent 4, 5, 6 years, he is asking constant heat flux. Constant heat flux is constant. At every location, you are imposing the same heat flux. Then the total heat transfer rate will be constant heat flux into pi dl. That is the area of heat transfer, where d is the diameter, L is the length of the pipe. That will be equal to the m dot Cp into Tb exit, bulk mean temperature at exit, bulk mean minus bulk mean temperature at inlet. See, this bulk mean temperature concept is very essential to understand in flow through pipes. Internal flows, Tb is a very important thing, bulk mean temperature. That indicates the temperature of the fluid, average temperature of the fluid at a given cross section, which keeps changing. If the fluid is getting heat, the Tb will be increasing. If the fluid is losing heat, the Tb will be decreasing. But Tb must change in the direction of the flow. Tb means at a particular cross section, how much will be the average temperature of the fluid. So this equation is applicable for all the constant heat flux conditions. So here for the constant heat flux situation, if you see here, the Nusselt number will be Hd by K 4.36. Here the Nusselt number will be 3.66. Nusselt number is Hd by K. Here in the laminar flow or turbulent flow, Nusselt number is a function of Reynolds number and Prandtl number. Here, see, in every forced convection heat transfer problem, forced convection I am talking, 3-dimensional S numbers we come, Nusselt number, Reynolds number, Prandtl number. First, learn the definitions of all the 3 numbers, Nusselt, Reynolds and Prandtl. Among the 3 numbers, most of the gate questions will be regarding the Prandtl number. Very so many times the Prandtl number questions have come. Give a more focus. Kinematic viscosity divided by thermal diffusivity, nu by alpha. Prandtl number is a property of the fluid. Prandtl number is the property of the fluid. Only dimensionless number in the entire mechanical engineering which is a property of the fluid is Prandtl number. Ratio between nu and alpha, Kv by Td. Td is thermal diffusivity. Nu by K by rho Cp, or otherwise mu Cp by K. So what is the benefit if you know the Prandtl number of a fluid? If you know the Prandtl number of a fluid, we can immediately tell which boundary layer, because we come across 2 different boundary layers. In most of the gate questions, they ask the Prandtl number in such a way that they give the Prandtl number value. Then they will ask you which boundary layer is thicker than the other. Whether hydrodynamic boundary layer is thicker or thermal boundary layer is thicker, we can immediately declare just by knowing the value of the Prandtl number. Okay. Say for example, air is there, Prandtl number is 0.69 or we take it as 0.7, that is less than 1. That means if the Prandtl number is less than 1, delta will be lesser than delta T. That means thermal boundary layer is thicker than the HBl. For water, Prandtl number is around 2 to 6, more than 1. That means delta will be greater than delta T. If the Prandtl number is 1, say for example 1, delta will be equal to delta T. So that is how they frame the questions. For mercury, Prandtl number will be very low because K is very high and Cp is low, but for mercury, Prandtl number is very low. So Prandtl number, by knowing the Prandtl number, you will be immediately declare delta is more or delta D is more. That is how they set the questions. Prandtl number is a ratio between, so many times the questions on Prandtl number have asked. In any forced convection, Nusselt number is a function of Reynolds number and Prandtl number. Supposing if it is a flow is turbulent here, this is all, this is for the laminar, all this is for the laminar internal flow. This is point that it is laminar internal. If the flow is turbulent inside the pipe, if the supposing flow is there, internal flow only. I already said, whenever you doing the problem, first geometry you decide, external flow or internal flow. If it is internal flow and the flow is turbulent, how do you know turbulent? Reynolds number is greater than 4000. Flow is turbulent, you decided. Reynolds number is Vd rho by mu. Okay, inertia force by viscous force. If the Reynolds number is greater than 4000, just apply this equation, 0.023 Re to the power of 0.8 Pr to the power of n. N will be 0.4 for heating, n will be 0.3 for cooling. For cooling of fluid, this is for heating, other thing is for cooling. Okay. This equation is also called as the McAdams equation or Dittus-Boelter equation, very famously known as Dittus-Boelter equation. Any turbulent flow inside the pipes, you can blindly use this. Nusselt number is Hd by K. Please note that in every convection problem, all the rho, mu, Cp, K, whatever the fluid property, whatever the properties are given, only that are the fluid only. Solid properties have no role. Okay. 4 properties must be given in all the convection problem, rho, mu, Cp, K. Okay. So this is how this is convection problems can be attacked. Okay. Easy only, not tough. But one must be very cleverly understand the problem. In the recent times, he is asking about the constant heat flux conditions flowing inside a pipe. How do the bulk mean temperature? See, for constant heat flux and for constant wall temperature conditions, the bulk mean temperature, the temperature variation, this for fully developed flow, you will clearly give fully developed flow thermally, fully developed flow hydrodynamically and thermally. There are two different aspects. A fully developed flow both hydrodynamically and also thermally. This is called entrance length. This is the temperature versus direction of the flow. This is a variation. This is a variation of the pipe wall temperature. This is the variation of the bulk mean temperature of the fluid, where the Hx value remains constant in the direction of the flow. Hx will not change in the direction of the flow. Unlike the flow over flat plates, there is a main difference. In flow over flat plates, external flows, internal flows, the main difference is in the flow over flat plates, the Hx value will be different at different locations, whereas for fully developed flows internally, the Hx will not change in the direction of the flow. It remains constant. Hx remains constant. But the pipe wall temperature and bulk mean temperature keeps increasing, but the delta T temperature difference between them remains constant. Delta T is not a function of x. What is the delta T? Tw minus Tb. This kind of questions they are being asked. This is only short distance, entrance length. Developing flow, it is called as the developing flow. This is fully developed flow. This is developing flow, that is fully developed flow. So these are the main highlights. We have to put an extra torch. In the convection problems, we have to put an extra torch. We have to put an extra torch in these particular topics. In these particular topics, then comes the heat exchangers. Heat exchangers is the easiest, but two methods, special cases and LMTD method, effectiveness NTU method. You have to understand because particularly parallel flow or a counter flow, what is LMTD formulae and what is the definition of the effectiveness, particularly when you are dealing the effectiveness, this m dot Cp, which side it is shorter, which side is more. M dot Cp is small on hot side or cold side. Hot side or cold side, that you first decide. That question mark first you decide. Based on that your formula, everything will change. NTU means number of transfer units. This is for LMTD is method to calculate area, just to design the heat exchanger, to calculate area. Effectiveness NTU method only this you pick up this method only to calculate both exit temperatures. Only to, if you only two inlets are given, you see I can say blindly like this. In any heat exchanger problem, if you are finding only two temperatures in the data, directly blindly go to the effectiveness method, NTU method. In any heat exchanger problem, if you are reading three temperatures in the data, directly come to the LMTD. Directly come to the LMTD. Okay. So that one should be able to distinguish between these two methods. Right. So this is all, but heat exchangers you can very easily answer, but some special cases try to understand. If one fluid is undergoing phase change, that fluid temperature will not be changing. Excuse me. If one fluid temperature, steam is condensing, temperature will not change. If water is boiling, temperature will not change. So that such kind of a special cases you have to understand. Whether one fluid is undergoing phase change, it does not matter whether you are designing a parallel flow or counter flow. Okay. And particularly there is one important case generally people will do. In counter flow heat exchanger, that will become a special case. In counter flow heat exchanger, if mass flow rate m dot h Cph, hot fluid and cold fluid will have the same capacity rate, then it will become the balanced counter flow heat exchanger. Balanced counter flow heat. In such cases, the temperature profiles will just become parallel. That is a very important special case. Very often this kind of a model being asked. Give an extra focus for that balanced counter flow heat exchanger, where the capacity rates m dot h Cph is equal to m dot c Cpc in a counter flow. Particularly this case is pertaining to the counter flow heat exchanger. Okay. So this is all about the heat transfer. Then coming to the applied thermodynamics, where we deal with power plant. Actually the weightage will be around 4 marks. In the power plant, most of the questions come from the steam power plant only. Rankine cycle. Rankine cycle, that too regeneration. Rankine cycle, again we have the two modifications here. With regeneration, give an extra focus for this regenerative Rankine cycle, and of course there is a reheat Rankine cycle. Regeneration is, I give the maximum focus, regeneration. Regenerative Rankine cycle, where bleeding, regeneration only we talk about the bleeding of steam. Live steam will be bled from the turbine, will be mixed with the water coming from the condenser, condensate coming from the condenser. And of course reheat Rankine cycle also important, but this is more important, regenerative. And again we have the gas turbine power plant. Breton cycle, this is easy, this is easier than the steam. In the steam power plant analysis or the Rankine cycle, we have to wisely pick up the data from the table. Here there is no table, we can, because gas turbine power plant working fluid will be air, which is an ideal gas. All the ideal gas relations you can easily write here, that is PV is equal to RT, or Cp minus Cv is equal to R. All those we could apply for the gas turbine power plant because it is running on Brayton cycle. Gas turbine power plant runs on the Brayton cycle, right? This cycle is the Brayton cycle. It may have the regeneration. Again, it may have the regeneration. It may have the reheating, etc. But with again, it may have the machine efficiencies. It will be a compressor. The compressor may be having some irreversibilities. Turbine may be having irreversibilities. What is the isoentropic efficiency of the compressor? What is the isoentropic efficiency of the turbine? Focus on that. Okay, this is quite easier as compared to the steam power plant. You can easily solve all these questions. We have to write the, say for example, if this is the 1, 2-2, by using the isoentropic relations we can calculate this temperature. By using the isoentropic efficiency of the compressor, that is T2 dash minus T1 by T2 minus T1. Usually this isoentropic efficiency will be around 0.85 like that, 0.9. We can calculate all the temperatures. Analysis of the Brayton cycle is nothing but just getting all the salient temperatures in the cycle. Once you get all the temperatures, you could easily calculate the thermal efficiency and work ratio. Only two things you need to calculate here: thermal efficiency and work ratio. Okay, what is work ratio? Turbine work minus compressor work divided by turbine work. In the gas turbines, three modifications will be there: reheating, regeneration and intercooling. There is again intercooling modification is there. Intercooling is the only word you get in the gas turbine power plants. Intercooling with multi-stage compression. Intercooling with multi-stage compression is done to reduce this compressor work. So that those three modifications led. That's all. That is a power plant. And of course, we have the refrigeration is there. Refrigeration and IC engines. In the IC engines, don't bother anything. Just study Otto cycle. Just study Otto cycle on PV plane to constant volume to isentropics. That's all. Just study Otto, nothing else, because diesel also is not being asked. And we have to know what is the clearance volume, what is the stroke volume, what is the compression ratio Vc plus Vs by Vc, and what is the thermal efficiency formula for the Otto, 1 minus 1 by R to the power of gamma minus 1. This is where R is called as the compression ratio. That's it, nothing else, because he is not going beyond that. Earlier gates they were asking very deep in the IC engines, but here nothing is more than that. Coming to the RAC, refrigeration air conditioning also, just focus on VCR cycle, vapor compression refrigeration cycle, nothing else. Don't have to study anything else, just study the VCR cycle, how to calculate the COP, tonnage, etc. Okay. Just know what is the COP, how to calculate the coefficient of performance, refrigeration effect divided by work input of the compressor. And recently more focus is being asked in the psychrometric chart. Psychrometric, particularly regarding the AC, the psychrometric chart, this is drivable temperature, this is specific humidity, these are RH lines. Give a focus for the psychrometric chart. Psychrometric chart and psychrometric relations, only two relations are there. Relative humidity is equal to PV by PS. Specific humidity is equal to 0.622 into PV by PB minus PV, where PB is the total barometric pressure, PV is the partial pressure of the water vapor, PS is the saturation partial pressure of the water vapor. PV is the actual partial pressure of the water vapor. This is the partial pressure of the water vapor at the saturation conditions at the same dBT. So this is RH, this is specific humidity. Only these two relations, if you apply these two relations and psychrometric chart, and 3 or 4 psychrometric processes, sensible heating, sensible cooling, cooling with dehumidification. That's all. We can answer any question, because they are not asking much in the, because weightage of the power plant engineering is only 4 marks only. 2 marks may come from the power plant, 1 mark from the IC engines, 1 mark from the RAC. So that is a rough weightage for the thermal and fluid sciences. Then coming to the applied mechanics and design, applied mechanics and design. Actually, that most important thing will be the SOM, strength of materials. Its weightage will be 8 marks, 7 to 8. Sometimes lesser, but usually 7 to 8. It is easy subject and interesting subject also. Simple stresses and strains. First topic, easy topic, where we have to we have to understand what is the direct stress, shear stress, and the volumetric stress, and the respective Young's modulus, shear modulus, bulk modulus, Poisson's ratio, PR, Poisson's ratio, that is mu. All these things, mu or some books will call it as a mu also. So relations among themselves, and stress strain diagram, a typical stress strain diagram for the mild steel, a ductile material. What are the important points, right? Right, elastic limit, limit of proportionality, upper yield point, lower yield point, ultimate point, and breaking. All these things we have to understand, and that we have to understand what is the strain energy. See, first chapter is quite easy in the strength of materials. Strain energy, proof resilience, modulus of resilience, or the toughness. If you learn these areas, yes, definitely out of 8 marks, 2 marks we can pakka answer, definitely. Strain energy, the energy stored inside the material, inside the body by virtue of the strain. Like when you elongate the spring gets elongated, but there is certain energy being stored in the spring. If you release the spring, and that energy would be able to do some work. Okay, like that, when an elastic member gets elongated or gets compressed, there is an energy stored inside that. Off into stress into strain, the strain energy stored, and strain energy stored per unit volume is a modulus of resilience, and again toughness, and what the area up to the elastic limit indicates something. The total area under the stress strain diagram is called as the toughness. All these things you have to learn, and the relations among them. E is equal to 2C into 1 plus 1 by m, where m is the 1 by m is the Poisson's ratio. E is equal to 3k into 1 minus 2 by m. E is equal to 9kc by 3k plus c. So the relations, 1 by m is the Poisson's ratio, PR. M will be usually for the engineering materials, it will be 3 to 4. Usually 0.3, 0.25 to 0.3, that Poisson's ratio value will be 0.3 or like that for a simple engineering elastic ductile materials. So this is the easy chapter and interesting chapter also, first chapter. Poisson's ratio definition. When an elastic member is subjected to the multiple like stresses or unlike stresses, one may be tensile, one may be compressive, what is the total change in the volume, and all these things in the first chapter. Then comes the SFD and BMD, shear force and bending moment diagrams for all the kinds, on cantilever and propped cantilever, okay, UDLs with the point loads, with UDL and various configurations, that SFD, BMD, shear force and bending moment diagrams for all kinds, simply supported beam, cantilevers, simply supported beam, and all the where you get the maximum bend, what is the point of counterflexure. So what is the relations, dm by dx will be shear force, and shear force by dx will be the rate of loading, this kind of a relations, and point of counterflexure, where the bending moment will be 0, where the bending moment will be maximum, where the shear force has changed its sign from positive to negative, all these things, and including the propped cantilever, overhang beams, propped cantilever, all these options, configurations one should know, that SFD and BMD, just give that important. Then comes the bending and shear stresses. This bending moment equation, m by I is equal to F by Y is equal to E by R, correct? Flexural rigidity, E into I is flexural rigidity. What is this product called EI? Okay, where you get the maximum bending moment, and what is the moment of inertia? Because in the recent questions he is asking the moment of inertia of different shapes actually. He has asked, I think, the one tapered member, he has asked the moment of inertia about this centroidal axis. He has, no, this vertical axis. What is the moment of inertia? He has asked. So that kind of things one should be ready actually. This is a bending stress. This is the distance from the neutral axis, moment of inertia, and the bending moment, Young's modulus. This is the radius of curvature or the radius of curvature of the bending. So the bending moment equation give a more focus. And shear stresses also. Shear stresses particularly, what is the shear stress variation in a cross section for a shaft, for a rectangular, it will be different for the different cross sections, for a square cross section, for a circular cross section. How do the shear stress variation with respect to the neutral axis, how do the shear stress changes from point to point in the cross section? That also one should know for various shapes. Then comes the deflections. Deflection slightly difficult, but remember for the UDL, for the cantilever, what is the deflection formula, what is the UDL, what is the max, where you get the maximum deflection and how much is the maximum deflection. And I give the maximum weightage to the Mohr circle in the shear for in the strength of materials, Mohr circle, principal stresses and strains. Mohr circle construction, that is I give the maximum weightage. Generally an elastic member element may be subjected to the direct stresses sigma 1, sigma 2 and one shear. This is the most general case, right? Tau. So this is how to at an angle on a plane at an angle theta, what is the normal stress, what is the shear stress, what is the principal stress, what is the principal plane? It is a plane on which there are no shear stresses. The only stresses that are acting over a principal plane are normal stresses. They are called as the principal stresses. And how much will be where is the principal plane, how much is the principal stresses, everything, how to construct a Mohr circle. That is give a maximum weightage. In the strength of materials subject, I give the maximum weightage to the principal stresses and strains apart from the simple stresses and strains. In the recent question, one of the asked a fluid element at static, a fluid element at a point in a static fluid, what is the radius of the Mohr circle? It is 0. Because when you are constructing the Mohr circle, x-axis indicates normal stresses, y-axis indicates shear stresses. And if you draw a fluid element at rest, for a fluid element at rest, there are only normal stresses, the two are compressive in nature. This is a hydrostatic pressure. According to the Blaise Pascal's law, the hydrostatic pressure is same. Therefore, when all the magnitudes of the stresses are same, the radius of the Mohr circle is 0. Therefore, Mohr circle reduces shrinks to a point. On the x-axis, a negative x-axis, I have put the Mohr circle because this is the fluid element at rest. It is a fluid element at rest, compressive in nature. So this kind of a questions may ask. So give a maximum attention to the principal stresses and strains. Then comes the thin cylinders, only two formula, hoop stress and longitudinal stress, thin cylinders, PD by 2T, only two formula, PD by 2T and PD by 4T. Just to learn about them. And then the Euler's theory of columns. If you break the syllabus, syllabus looks easy to study. The main psychological component about preparation is you break the syllabus, subject into subtopics, topics into subtopics and micro topics. If you break it, that the preparation becomes easy and preparation becomes interesting also, because as you are reading the question, your mind also will be programmed to pick up to solution according to the topic where the question was given. When you are reading the question, your mind will be automatically tuned to which subtopic you have to go in that direction and to You have prepared something, so yes, immediately you will be able to read, yes, this question belongs to that particular subtopic, and where the question is, concept is underlying, and you will be pick up that. So that kind of a recollection of the data, recollection of the preparation what you have already done becomes easy if you divide the subject into topics, subtopics and micro topics like that. In the Euler's theory of columns, only crippling load formula for the 4 cases, one end hinged, one end free, both one end fixed, one end free, both ends are hinged. Those 4 formula you remember, crippling load formula, and slenderness ratio. Slenderness ratio, that long columns, theory of long columns. 4 cases are there in the Euler's, 4 different kind of cases. Both ends of the column are hinged. One end is fixed, one end is free. One end is fixed and another end is hinged. So comparison of the crippling load, definition of the crippling load or buckling load. Okay. So that is, and apart from that, you have the theories of failure. In the theories of failure, only totally 5 are there. Main important thing are Rankine theory, maximum principal stress theory, Rankine theory, and then the second important thing is von Mises distortion energy theory. The very often it is being asked, von Mises theory, and Tresca's theory, maximum shear stress theory. So 3 theories are important, 2 are not that important. These 3 theories of failure, Rankine, von Mises distortion energy theory, and Tresca's theory, maximum shear stress theory. And which kind of material that theory is applicable. Some theories are applicable for the ductile materials, some theories are applicable for the brittle materials. So which theory is applicable to what kind of material, try to understand. So this is the entry into the design actually. From here, theories of failure only, you will enter the machine design. Machine design is a design of shafts. Actually in the design of shafts, again the torsion equation, this torsion is the important topic in the SM, where the torsion equation T by IP is equal to Fs by R is equal to C theta by L. This is the torsion equation. Of course, in the strength of materials only this torsion should be studied. We can combine with the design of shafts also, machine design. Design of shafts, design of bolts and welded joints. That point, give an extra high focus to these areas. Usually machine design weightage will be 3 to 4 marks. Fatigue and fatigue strength. Fatigue strength. These are the important topics where you have to give more focus in the machine design. Then in the engineering mechanics, free body diagram, equilibrium. Free body diagram and equilibrium. That is a very important. That is applying that 3 equations of equilibrium. Sigma fx is equal to 0, sigma fy is equal to 0, sigma m is equal to 0. When a body under a static equilibrium, how to write the 3 equations of equilibrium. How to construct a free body diagram, equilibrium and plane trusses. Okay. Virtual work also is there, but in the recent years the trusses questions being asked very often. There is a virtual work. And the most important topic here will be impulse momentum collisions, impulse momentum equation and work energy theorem. Give a more focus on this. And friction also. Friction. Easy, friction is easy. Belt friction or wedge friction, or supposing a body over body. Supposing there is one body here, there is another body. This is being pulled. This is being pulled like this, body over body. That these kind of questions are asked in the coefficient of friction, how to apply the law of friction there. Okay, in which direction the frictional force act, all these things, and also the rolling friction. Friction means that comes the rolling friction also. Translation and rotation. Of bodies, that is when a wheel is rolling, supposing a wheel is rolling from an inclined plane, if the if a wheel is hollow, a wheel is solid, which will go down the fast. Maybe a wheel is rolling and sliding over the inclined plane. If it is a hollow, having so and so moment of inertia, mass moment of inertia, which will reach the bottom fast, the time taken by the hollow and the solid one. So we must have learned all these things in physics also. In the 11th class or 12th class physics, engineering mechanics is an extension of the physics, what you have learned in 11th or 12th class, right? But in the engineering application mode. So this is all about the applied mechanics and design. Then the manufacture, when you talk about the manufacturing and industrial, I give the maximum weightage first to the machining and machine tool operations, where orthogonal turning, where you deal with the merchant circle cutting, mechanics of the metal cutting, merchant circle, construction of the merchant circle, and calculating the cutting forces, shear angle, shear plane, ASS system, and shear plane, shear angle, rake angle, and how to calculate given the cutting speed, what is the cutting force required with a so and so depth of cut. That all that will be the definitely 2 marks will compulsorily will come. There it is the very often these questions, Taylor's tool life equation. V to the power of n is equal to constant. No? This is being asked very, very often. Taylor's tool life equation. This 25 also I think is asked on that, K25 also. First thing, I will give the maximum weightage to the orthogonal turning and analysis of the mechanics of the metal cutting by using the merchant circle with the reasonable assumptions, with the relevant assumptions. Okay. Then comes the casting. Actually, in the casting, most important topic will be solidification time. Based on the shape of the object, and solidification time is proportional to the, you will give the volume, you will give the area, the exponent will be there, V by A to the some power of some exponent will be there, solidification time, and you will give the one cylinder will be there, one sphere will be there, comparison like that. So that is very often being asked in the casting. And casting defects and mold components. And the time taken by the molten metal to fill the runner or riser, that by using, so again the Bernoulli's equation etc. concept there. So runner riser design, that is very commonly being asked in the casting part. Casting, usually manufacturing weightage will be around 16 marks out of the 24-25 marks in the manufacturing industrial. Manufacturing will comes around 16 marks, which contains machining, casting, welding, forming, metrology and inspection. Okay, these are all the 5 topics, and SIM, computer integrated manufacturing. All put together it will be around 16 to 17. I repeat, machining and machine tool operation, which includes shaping, orthogonal turning, all that, casting, forming, welding, and metrology inspection, and of course engineering materials. Engineering materials, one question may come, that is metallurgy. One question may come, or sometimes it may not come also. Total weightage there will be around 16 to 17 marks. Then comes the forming there, cold working, hot working, the force required for so and so drawing operation, extrusion. Okay, all these few marks will be coming there, and then welding there. Welding will be voltage or characteristics. That is an important topic where you have to focus more. And energy density. The 25 is asked on the energy density of the welding there. And metrology inspection. Optical flat, metrology sign bar, optical flat, go, no go, optical flat, go, no go, gauges, measurement of the angle, no. All these things in the metrology inspection they may ask. Then comes the industrial engineering. Its weightage will be around 6 marks. And most important topic I give here, the PET and CPM. PET and CPM is the most critical path method, program evaluation review technique. So that very, very important topic among the, and then comes the linear programming. Sometimes transportation may also, but linear programming is another important thing. And then comes the economic order quantity, inventory cost, ordering cost, total cost, inventory and control. So these 3 topics I give more weightage in the industrial, which comprise around 6 marks there. If you are able to identify those areas, give an extra time during this 1 month preparation. Okay. Sometimes questions come from the transportation thing, also forecasting also. Sometimes question may come from the forecasting also in the industrial part. Production planning and control, no? First topic will be the forecasting only. Okay, so this is the weightage will be around 6 to 7. That there comes to around 17 marks in the manufacturing, comes to around 24 to 25 in the manufacturing and industrial. Of course, mathematics, all topics are important, but more important topics are differential equations and calculus. Linear algebra also they will come, 1 mark will come in the linear algebra, and differential equations and calculus. Never take a chance. Probability statistics slightly difficult, but 1 mark may come in that. Probability statistics 1 mark, differential calculus, total weightage for the mathematics is 13. Each topic will be 1 and 1 mark, but more marks may come from the differential equations and the calculus. That is and probability statistics, these part. Okay. And of course, aptitude will be 15. So if you are thorough with the mathematics and aptitude, and if you are able to score out of the 28, if you can reach reasonably up to 18 or 17 like that, in the engineering 72 remaining, say if you are able to touch around 35, 40, 35 plus 17, if your score goes above 55, 60, 55, yes, you are sure of getting a good seat in a reasonable IIT or NIT, good NIT. So don't lose the heat, actually maintain the tempo till the 1 month time is there, and whatever the areas I told, and refer to the previous papers, at least from 2020 to the 2025, last 5 years. Keep reading all the questions, try to solve on your own. After completely preparing each subject, pick up one subject. All the last 5 years questions, try to attempt on your own, okay, without referring to the solution. Your temptation will be to go to the solution, don't go to that. You let it take more time, but try to attempt that, okay. And whatever the relevant formula, write on a small slip, because that may help in the last 1 week preparation. It may help all the relevant formula to try to write, and important precautions also pertaining to that concept you try to write, so that error can be minimized while attempting the problem, okay. And don't try the new topic. I advise not to take a new topic, because in the last 1 month, if you try to take a new topic, it will waste a lot of time. So whatever the topics you have learned, and supposing if you have learned about the convection chapter, say for example, so I have given you some important topic, focus for important topics where you have to focus more. Pick up those topics, try to solve more problems from that. Okay, particularly for the last 5 or 6 years of GATE paper, because humans only will set the paper. They will take the previous papers. Question will not be repeated, no doubt, but the concept underlying the problem will be repeated. So that is how you can how to utilize this last 1 month. And any doubt you are having, you may contact me. This is my number. You may call me and ask me also. You can WhatsApp to me also. You are welcome. But don't leave the tempo. And again, I will be coming to you. I will be meeting you on the February 8th with the solutions and analysis of Engineering Services ESC 2026 paper prelims. That will be quite. That obviously that will be quite easier than the GATE. But anyhow, that if you write that ESC paper also, definitely it will be useful, because exactly after 1 week you have the GATE examination, right? That will be, I can think of that as a practice exam for the GATE. Definitely ESC paper will be quite easier as compared to the GATE. Okay. The standard of ESC, number of topics will be more, but the depth of the questions will be quite easier as compared to the GATE. Okay. But I will be meeting you again with a video on February 8th with ESC prelims paper. With this, I would conclude. Good luck, all the best.